The lexical functional theory of grammar was developed in collaborative research at the Xerox Palo Alto Research Center and the Department of Linguistics and Philosophy at MIT. The theory of grammar was specifically aimed at satisfying three goals. First, we wanted a syntactic formalism that was linguistically adequate. That is, it could be used effectively by linguists to describe and encode the kinds of significant generalizations that natural language grammars aim for. Second, we wanted it to be psychologically adequate. We wanted it to be naturally incorporable into a competence-based theory of human syntactic performance. And third, we wanted it to be computationally adequate. We wanted it to admit of efficient and natural computational interpretations to be used for a variety of perhaps practical natural language processing tasks. We have, in fact, constructed an initial implementation of the lexical functional theory in a system which we consider to be a grammar writer's workbench. This is a system that is aimed specifically to be a tool that linguists could use to construct and debug natural language grammars. It is not, at least this initial implementation is not, a system aimed at psychological modeling or even designed to be particularly efficient as a computational engine. What it does do is enable the linguist who doesn't know programming and doesn't want to know programming, doesn't care about particular sequences of processing steps. It enables that linguist to deal at the competence level, to deal with the grammars and the linguistic representations that the grammars define for sentences without really being overwhelmed by the details of the particular processing algorithms that might be involved. This particular system is a parsing system. It's a system in which the linguist can type in a sentence. The system would contain the current state of a grammar that the linguist had defined. When the sentence is typed in, the grammar is applied to that sentence to produce the various levels of representation of the LFG theory. This implementation is done on a Xerox 1100 personal Lisp machine in the programming language or the programming environment Interlisp-D. That's an extension of the Interlisp programming system that's widely used on PDP-10 computers. The D implementation of that programming system extends the environment to include the display capabilities that you see behind me. We see a large format bitmap display and this mouse pointing device, which I can roll around on the table and cause a cursor to be moved around on the screen. In this way, I can point at various regions of the screen and click one of these three buttons to cause various events to take place. I'd now like to demonstrate this Grammar Writer's Workbench to you. What you see now is the display stream of a Dolphin computer. On the screen, you can see a cursor moving around. It moves as I move a mouse pointing device around on the table. The mouse has three buttons on it, which I can use to indicate certain kinds of actions that the system is to perform. Up in this window here, the top window, is where we can type in sentences, such as the very simple sentence, the girl devours the banana. When I type this in, the system will now reconfigure itself into its working configuration. Those headlines came down, and a number of other so-called windows came up. This window here is what we call the constituent structure window, or C structure window. It displays one of the two levels of grammatical representation that LFG grammars assign to strings, the surface constituent structure. Here we see the surface structure, a standard linguistic surface structure for this sentence, the girl devours the banana. We see noun phrases, verb phrases, and so forth. There's nothing surprising about this. And for every sentence of a language, LFG would assign one or more surface structures or C structures, more than one if the sentence is has a surface structure ambiguity in it, none if in fact the sentence is ungrammatical at the surface structure level. In the lower window here, we see the other level of representation that LFG assigns to strings, the other syntactic level of representations. There are in fact other levels that have to do more with the semantics and semantic interpretation. What we see in this window is the functional structure, or F structure, for this sentence. A functional structure is a list of pairs where the left-hand member of each pair in this column, for example, is the name of a grammatical function or feature. We see here subject, tense, predicate, object. In the right-hand column, we see the values for those attributes, features, or functions for this particular sentence. So we see here that the value of subject for this sentence is something that has, it's another F structure, a subsidiary F structure, that has the feature case with value nominative, the feature specifier or spec with value the, person with value third, predicate with value girl in quotes. Similarly, we see that the object is a subsidiary F structure. The predicate is devour. It's in quotes. The quotes indicate what we call a semantic form, a specification that drives the semantic interpretation. It represents the predicate argument relations of the sentence and the mapping between the surface grammatical functions, subject and object, into those predicate argument relations. In this case, we see that the predicate of this sentence is devour, which is a two-place predicate. The first place corresponds to the eater or the agent of that predicate. The second position corresponds to the theme or thing eaten, that semantic argument of the predicate. And we see for this particular sentence that the subject, girl, in fact, this F structure here, is in fact assigned as the first argument of the predicate, as the agent, and that the second argument, the thing eaten, is in fact the banana F structure. This notation here, we have an index with a predicate name. That index is the same as the index associated with the fully expanded printout of that F structure. This is just an abbreviation to indicate that in fact it is this particular object, F structure, that is filling that semantic role slot. So these are the two levels of description. The one surface structure that would be subject to phonological interpretation, say, and the F structure that would be the domain of semantic interpretation, rules of anaphora, reflexivization, pronominalization, and so forth. One other distinction between these two levels is that the F structure is in fact in a universal format. The labels subject, object, tense, predicate, and so forth have universal significance, would appear for similar sentences across the languages of the world, whereas the surface structure here is a very English particular level of analysis. And sentences in other languages, for example, that don't have verb phrases or don't even have constituent structure would have radically different C structures for a sentence like this, but the F structure would be essentially the same. It would show a two-place predicate mapping the subject and the object onto the various arguments. Now, what a lexical functional grammar does, and a lexicon, of course, is in fact provide a mapping between the surface structure and the F structure. And we can get a sense of that by considering the following properties of the theory. The first assumption is that for every node in the C structure, there is a corresponding F structure. If I go up to this button panel up at the top of the screen, this has a number of labels on it. This is an active region of the screen. When I hit this button, I'm hitting the left button on the mouse. The tree gets redrawn, and this time we see indices associated with the nodes of the tree. And these indices are in effect the same indices that we see labeled down in the F structure. In fact, if F structure 21 is the F structure associated with the S node, F structure 9 is the F structure associated with this subject noun phrase node. And if we look down in the F structure window, we see 21 labeling the outermost pair of brackets, 9 labeling the subject. In fact, this is the F structure that's derived from the noun phrase NP up in the C structure window. And the larger complete F structure here is, in fact, the F structure associated with the outer S node. Now, the way the F structure with these indices is assigned to this string is by a set of equations, an algebraic set of equations that are associated with the nodes in the tree, and which in fact specify what the F structure associated with that node is to be. If I point at this node and click the mouse button, another window will open up over here to the left, which is the functional description window, or F description window. And it in fact is displaying the set of equations, the algebraic set of equations that the grammar is associating with the S node, and which describe all the properties of that S node's F description, F structure. In fact, the F structure can be thought of, and is, the algebraic solution to the set of equations in an F description. So for example, if we compare the F description window with the F structure, we see the first equation here that says F21's subject, this parenthetic notation we read as a kind of possessive or functional application notation. So we say F21's subject is equal to F9. If we find 21 in the F structure, find what it's assigned to, what it's associated with, we find it's the outermost F structure. We find its subject, its value, that's this thing, and we notice that in fact it's labeled 9. In fact, it is true that F21's subject is F9, and this equation, the first equation in the F description, is in fact satisfied by the F structure over on the right. Similarly, F9's case is nominative. If we find F9, we look for its case. It is indeed nominative. That equation is also satisfied. In fact, all the equations listed in this F description are true of this F structure, and that's why it is in fact the F structure for this sentence. Now, where do these equations come from? Well, associated with the constituent structure rules of the language are functional schemata. And we can look over here. We have a menu of categories that are in our current grammar. I'll point at the S. And what we see in this window now is the actual grammar rule for S that was used in deriving the structures for this sentence. We see the constituent structure part, S goes to NP VP. That's a standard context-free rule. And of course, if you go back into the C structure window, we see S goes to NP VP. So in fact, the node S does satisfy the conditions of that rule. However, back in the rule, we also see these annotated equations on the symbols. We see on the NP, we see up arrow subject equals down arrow, and down arrow case equals nominative. The way the formalism works, when we derive a node using this rule of grammar, we associate these schemata notionally with the symbol that, the grammatical node symbol that they are associated with in the grammar. In other words, up subject equals down would be associated with the NP node here. And the up arrow is then interpreted as the value of the F structure variable, the algebraic unknown that stands for the F structure of the mother node, in this case F21. That gets substituted in for the up arrow. F9, the algebraic variable representing the F structure of this NP node, that gets substituted in for the down arrow. Given that we have F21 and F9 in this configuration, performing this so-called instantiation of the rule schemata, we get the first equation, F21 subject equals F9. From the equation or schemata over here, down's case equals nominative, we get, for that NP, F9's case equals nominative. Looking back at the VP rule, we have up equals down, where on the VP node, again looking back at the tree, we see that the up arrow is 21 and now the down arrow is 16. That gives rise to the equation F21 equals F16. Now that might seem to be a peculiar kind of equation. It's basically saying that even though we have two algebraic variables corresponding to the two different nodes, F21 and F16, there is in fact one F structure that they both refer to. In other words, there are two ways, two methods by which we might gain information about that F structure, either by seeing equations framed in terms of F21 or equations framed in terms of F16. But clearly, because of the substitution axioms for equality, we can substitute 21 for 16 wherever we wish. And in fact, the only way that that equation can be true of an F structure is if all the specifications about F21 and all the specifications about F16 are true of exactly the same object. And if we look again at the F structure over here, the reflex of that is that 21 and 16 label exactly the same F structure. The effect of this in the F structure is that the subject and object come out as being at the same level in the functional hierarchy, even though, of course, the object in English is embedded underneath an NP. The object NP is embedded underneath the VP and is not a direct daughter of S. This equation, F21 equals F16, effectively flattens out the F structure, letting us semantically treat subject and object in a uniform way. Clearly, for languages that don't have a VP constituent, we would want an F structure like this. An equation like F21 equals F16 or up equals down gives us the same or similar F structure for languages even where there is a surface but not functional unit for the VP. Now, that's perhaps enough introduction to the lexical functional theory. The theory itself is now well documented in a book from the MIT Press in a quite substantial number of papers. What I want to now turn to is some of the properties of the system that is, as I said, a grammar writer's workbench. And the goal of this system is to make it convenient and easy for a grammar writer to design a grammar, test it out, discover what problems it might have, demonstrate that it is in fact working correctly. In fact, the grammar that I'm using, not only is it small and trivial for the sake of demonstration, but it actually has some obvious errors in it so that I can illustrate how the tools in the system could help a linguist to come to understand what the problems are and come to repair them. Let me type in another sentence up in the sentence window. This is a simple intransitive sentence. The girl sleeps. When I typed in that sentence, the windows for the last sentence got cleared, and it parsed the new sentence and discovered, in fact, we see, of course, that the windows are still clear. The symptom that we see indicates that, in fact, there were no C structures for this particular sentence. We see 0 C structures here. The windows are all clear. Immediately, that indicates to the linguist that there is something wrong for this sentence with the C structure part of the grammar, the actual context-free parts of the rules. The question now is, how is the linguist going to discover exactly where the defect is? Is it a problem with NPs? Is it a problem with VPs? In order to discover that, the linguist needs to be able to inspect more details, what constituents were identified in order to discover what expected constituents were not. If we go back up to the button panel, we can ask for more detailed information about the constituent structure analysis by asking for an internal data structure called the chart to be displayed, and we see that over in the chart window that's now come up. The chart window illustrates or portrays all the constituents and partial constituents that were in fact identified in the course of parsing. What we see across the bottom here are the words of the sentence, the girl sleeps, with the junctions between words labeled as vertexes in a graph. And we see other edges in this graph representing the constituents. So here we see that there's a determiner going from 1 to 2 that in fact is in parallel to the actual lexical item the. That says that in fact the stretch of string between 1 and 2 can be analyzed as a determiner, and we can point at that node and see over in the C structure window the subtree subtended by the determiner. In this case, we see clearly that the determiner dominates the lexical item the. Above that, we see a partial NP. Partial is indicated by the slash in front of the symbol. And if I ask to see the display of that tree over in the C structure window, we see that the partial NP does in fact dominate the determiner. But over here to the right, we see the symbol N not connected in any way to the NP. That indicates that this node, this partial NP, requires a following N in order for it to become completed, or at least to advance towards completion. We see back over here in the chart window that the NP, the partial NP, is in fact followed in the string by an N, and we see a complete NP now that spans the partial NP and that N, and indeed we now have an NP, it's complete, there's no continuation required, that does incorporate the determiner and the noun. So we see both complete and partial noun phrases, partial constituents. When we see the partial constituents, we see an indication of what the grammar says they need to advance further. Now, that subject noun phrase, that initial noun phrase, is in fact directly incorporated into a partial S. We see over here the S needs a VP to be completed, as one might expect for English. We look back here in the chart and we see that there's, following the partial S, there's a verb, there's a noun, there's a partial VP, but there's no complete VP. We look at the tree structure of the partial VP, and we see, in fact, the source of the difficulty. This is a partial VP that's incorporated a verb, is requiring a noun phrase to be completed. Okay, we can look at that noun phrase in a little bit more detail. We can see what equations are associated with it in the F description window, and we see in fact that it's the object noun phrase that's required. Now this is obviously an error in the grammar because English sentences do not require object noun phrases. That's an option. We know that the problem is in the VP rule because that's where we're looking at a partial VP. I can go over to the menu of categories and select VP by pushing down on one of the mouse buttons. And now we'll see the VP rule in this window. We see the VP goes to an optional not with a particular set of equations, a verb. And here we see the object noun phrase. And indeed the problem is that it's not optional. Now this is in fact a text editing window, so I can now point at positions in the rule and actually fix the rule right here by typing in the optionality parentheses. I install that rule, and we can now redo the analysis of this sentence. I just typed in the command to the sentence input interpreter, simply saying redo the last parse. And now we in fact see much more information on the screen. We first of all do find a C structure, just as one might expect. We see below it the F structure that one might expect, that in fact sleep is a one-place predicate of its subject. And if we look over in the chart window, we see not only a partial VP, but also a complete VP. And if I look at this partial VP, look at its continuations, we now see that there are many more possibilities. In fact, because we now made the noun phrase optional and all the constituents beyond it in the rule were optional, we see that the star indicating that that's enough. One option for this grammar is that a VP can be completed just after finding a verb. The noun phrase is still now an option to be taken, but also if it's not taken, we can see immediately following the verb prepositional phrases and verb phrase complements. So here we see through this little exercise one set of mechanisms that this grammar writer's workbench provides for helping the linguist to uncover and repair one possible kind of grammatical bug, namely a bug in the C structure component. Now, lexical functional grammar theory defines other conditions for grammaticality, functional conditions, that a string and its F structure, its F description must satisfy in order for the sentence to be judged grammatical. One condition, of course, is that it must have a C structure, as we've seen. It must also have an F structure. And let me type in a sentence that violates that condition, namely, him sleeps, an ungrammatical sentence of English. We do find a C structure for this sentence because, in fact, him or other pronouns are in fact nouns, and nouns can be noun phrases without determiners and so forth. So we have him sleeps as a C structure. But if we look in the F structure window, we find that there are 0 F structures in this little summary here. 0 F structures means that the set of equations that was derived by instantiating the grammar and the lexicon for the various nodes of the tree, that set of equations was inconsistent. There was no algebraic solution. We can ask, by going up to the button panel again, to see more detail about the inconsistencies. We, in fact, might have expected this inconsistency. In fact, we did in this case, because this was a bad sentence of English, and we might have just been confirming that fact. And in that case, we might not want to see more detailed information. But if this had been a surprise to us, we might have wanted to track down just what was the source of the inconsistency. by turning on the inconsistency display, we can in fact see more information. And indeed what we see is the annotation here that says there was an inconsistency. The equation F6's case equals accusative was inconsistent because at the time that the algebraic equation solver algorithm was applied, F6's case already had the value nominative, and nominative and accusative are not equal, are distinct. We can, by pointing here, ask to see the set of equations again with the particular inconsistency highlighted. So here we see this is the equation F6's case equals accusative, and indeed above it we find another equation F6's case is nominative. This one, of course, came from the S rule because it was the NP in the subject position, and we've already seen that. This one came from the lexicon, and I can ask to see the lexical entry for him over in the lexicon window. And here we see that him is a noun that shares the various root properties of he, but has the further equation that up's case equals accusative. Now notice this notation is exactly the same as the notation that you see in the rules of grammar, and in fact the treatment of schemata, equation schemata in the lexicon and in the grammar is completely the same. The same formal mechanisms of instantiation, the same solution algorithm. And indeed, a lot of the work of characterizing agreements, characterizing concord of one sort or another is carried out by means of equations that come either from specific lexical entries or from the morphological affixes that are attached to those entries. Okay, so here's a case where there was an ungrammaticality due to an inconsistency in the algebra here, and the system in fact helps us understand where that's coming from, how to track it down. There are two other, or three other actually, kinds of grammaticality conditions, ways in which a sentence can be defective, that involve functional conditions. And I can illustrate these by the use of some other sentences. If we say, the girls sleep, okay, which is a violation of subject-verb agreement, we find over here that the C structure is, as you'd expect, no surprise there. We find that there were two F structures, but none of them had good constraints. Now, how can there be multiple F structures for a sentence? Well, there can be disjunctions in the set of equations associated with a node. And we see these indicated by the curly brackets, the vertical bar separating the arms of the disjunction. And we see here that because, in fact, sleep is a root form of a verb in English, that there are some options here. We see that it is either infinitive, it has the infinitive feature with value plus, or it's tense present, and in the case when it is tense present, it must not be the case that the subject's number is singular and the subject's person is third. So we see the agreement morpheme, see its effects here. When these disjunctions are multiplied out into simple sets of conjuncts, we in fact get two conjunctive sets of functional descriptions. If I go up and ask to see more information about the bad constraints down in the F structure window, we can see how those two different conjunctive sets give rise to two different F structures. In the first case, in fact, we get two different F descriptions. We're putting this in disjunctive normal form before we apply our solution algorithms. We see here a sentence that has the infinitive plus feature. And if I point at this, I can see over here the particular selection among the alternatives that was used to produce this particular F structure. And we see indeed that the equation infinitive equals plus was chosen on this branch. That's why we have the infinitive plus feature. But there was a constraint that we see listed at the top of this window that says F17's tenths. Now this is a schema, but it's not an equation. It's simply a specification of the fact that the tense feature must exist for this sentence, although we don't care what its value, the grammar doesn't care what its value is. This particular so-called existential constraint is coming from the S rule, which I can display for you again by buttoning the category menu. And indeed on the VP we find that there is an existential constraint that the F structure of the mother node must have the tense feature. And going back to the F structure window, given that we chose the infinitive reading of this verb, this constraint is not satisfied. So that's why this F description is not reason to judge the sentence grammatical. Now, we can look at the bottom F structure by scrolling it up, and it has bad constraints. Its bad constraint is that the subject-verb agreement condition was not satisfied. Here we have in fact chosen the present tense reading that carried along with it the requirement that the subject's number of person not be singular and third respectively. And if we look at the F structure, we see that the person is third and the number is singular. So we see a violation of subject-verb agreement reflected in the failure to satisfy these constraints. Now, that's one kind, or another kind of functional condition on grammaticality. Two other conditions have to do with matching up the valence of the predicates with the grammatical functions that actually appear in the functional structure for the sentence. And if we get a mismatch, like the girl devours, okay, devour being a purely transitive verb in English, we see, again, the perfect C structure. We go into the F structure window and we see a diagnosis that says there was one F structure. It was not complete and determinate. I can now turn on more information about that from the button panel at the top. Show me the incompletes. And we see down here that devour is a two-place predicate from the lexicon. The second argument is in fact the subject. That's fine. The third argument is an underline, an indexed underline. That's a placeholder symbol indicating that in fact there was no specification in the surface structure for that argument, and in fact we see that it should have come from something from specifications framed in terms of the object, because we see the same indexed placeholder in both places. Now this could, in fact, if we expected this to be grammatical, this would indicate that there is a bug in the lexicon. We could go in with our lexicon editing window and fix that. In this case, in fact, we are happy that this comes out ungrammatical because, of course, it's an ungrammatical sentence. The other side of this is too many arguments for a predicate. And here is a sentence with an extra argument, and we see that it's marked as not being coherent. The coherency condition, I'll turn on again more information having to do with violations of that condition. The coherency condition simply requires that if there is what we call a governable grammatical function in the functional structure, then the local predicate, in this case sleep, must in fact take that and bind it as an argument. Must in fact, not necessarily bind it as an argument, but must in fact specify that grammatical function can be filled for the sentence. In cases of raising verbs, it's not an argument, but it is governed, as we say, by the predicate, because it's in fact mentioned in the lexical entry for that predicate. In this case, we see that sleep is a one-place predicate, and there is an extra unbound or ungoverned object. Now, these two conditions of completeness and coherence together, in effect, handle subcategorization phenomena of natural languages. It's noteworthy that in lexical functional grammar, these conditions are handled by, at the functional structure level, by requirements on what functions may or may not appear in the sentence, and not at the categorical level. The predicates, lexical predicates, do not say that they must or must not be followed by noun phrases, verb phrases, or whatever. They simply say what functions they require, and it's left up to the surface structure grammar to encode those functions in particular surface structure patterns. This should give you, this brief demonstration should, I hope, give you a feeling of some of the central properties of the theory, what the representations are, how they're determined and defined, and also give you a sense of how we put the high bandwidth and mouse pointing capabilities, display capabilities, to use in providing an interface that a linguist might find comfortable, a linguist who doesn't know Lisp programming, doesn't want to know Lisp programming, but still that linguist can easily and intuitively get a good sense of the representational structures, the linguistic structures that his grammars and lexicons have caused to be associated with the strings. As I said at the outset, this system is a grammar writer's workbench. It's not a system specifically aimed at modeling psychological processes or being particularly efficient computationally. In fact, one of the interesting things about this system is that it highlights the conflict that there can be between the needs of a linguist and a linguistically oriented system and the needs for efficient computation. To be computationally efficient, a system like this, a parsing system for lexical functional grammars, should really be computing the functional conditions of grammaticality at the same time that it's doing the constituent structure parsing. Those two levels of computation should be interleaved so that bad paths can be truncated as early as possible. But if we were in this system to reject a constituent that was otherwise valid merely because its equations became inconsistent, the linguist would have no way of knowing whether the problem was in the constituent structure part, that is, whether or not the constituents could in fact have been constructed, or whether the problem was indeed in the functional part. In order to help the linguist really partition the problem to the right part of the grammar, it's very important that each of the parts of the grammar be computed and treated independently. Now, we do intend, of course, to go on and produce computationally oriented systems. That's not a hard problem, but it is a problem, a system that would have very different goals and a somewhat different structure than the system that we demonstrated for you in this presentation.